All right, well, it's 7 o'clock, so we can go ahead and get started. For those of you guys just coming in, make sure you mute yourselves. If you've got any background noise going on, you can unmute yourselves and ask a question. That's totally fine. Also, you can send me a chat. I've got the group chat pulled up on the side, so I can go ahead and see those. And periodically, I'm going to ask you guys if you can just type out your answers for certain problems, just so I have an idea of everyone's working pace. All right, so the date is 6/6/2016. Doing some Calc 2. All right, so I have here the first problem that we're going to be doing. So go ahead and get a piece of paper and give yourself about 3 minutes to do this problem, and then we're going to go over it. So all I want you guys to do is transform this square root of 4 minus 9z squared into something that involves trig functions. That makes this a lot simpler. To get rid of the radical, that way, when we start looking at integrals that have this type of form, we can use trig sub to solve them. So we're starting to get a few more people joining in. Make sure that if you've got some background noise or anything like that, to mute yourselves. But if you have any questions, feel free to unmute yourselves to pose the question or use the chat. And we're just working on this first problem, and then we're going to go over the answer in just a little bit. All right, so let's start going over this. Well, to begin this, we know that we're supposed to be using trig sub here. So why don't we start with the good old identity, sine squared theta plus cosine squared theta equals 1, right? And we can use this guy. So we're going to rearrange this to look like 1 minus sine squared theta equals our cosine squared. So all I did was move the sine over. And this starts to look like what we might have in the radical. So we've got a constant term minus something that's squared. So what we're going to do is we're going to figure out what we need z to be in order for the constants to be the same to be able to apply our formula. So if we go ahead and set z equal to 2/3 sine theta, and we plug this guy in, this radical now becomes the radical of 4 minus 9 times the quantity 2/3 sine theta, and that guy's squared. We're going to complete the radical here. So now we're just going to go ahead, simplify a little bit. We've got 4 minus 9 times 4/9 sine squared theta. And of course, keep simplifying. We've got the radical. We're going to pull out this 4 here, so we've got 1 minus sine squared theta. And then we finish the square root. And then finally, we can pull out that 4 out of the radical, and it becomes just a 2, right? And then that 1 minus sine squared, what we talked about up here on this line, we're going to apply that to this guy here. And now we've got cosine squared theta here. And then we're going to have our final answer, 2 times the absolute value of cosine theta. So the reason it's absolute value is because we're squaring this thing and taking the square root. And we don't know too much about what theta is, so we can't make an assumption that cosine is positive. So we're going to have to keep those absolutes there. Okay. So we were able to convert our original problem, this guy here, into something that involves a trig function. Now, this helps with integrals because sometimes we'll have something in a weird radical that we can bring into this like trig-like space and be able to do the integral. So it's pretty much like a U substitution, except keeping in mind all of the trig functions' relations to each other. In this case, we were using the sine squared plus cosine squared equals 1 identity. Okay. So I'm going to go ahead and write another problem down and give you guys a few minutes to work on it. So, okay. Radical minus. So we have the integral of 1 over the radical of 9 minus x squared dx. So go ahead and take a few minutes on that. Once you think you have a final answer, go ahead and type it out in the chat. You can write it to everyone, or you can select the option to send it to me privately. That way, only I can see it. Up to you. All right, so we're starting to get some answers. Give you guys a little bit longer. Don't worry if you don't finish by the time that I start going over it. Continue to work, and then just check your answers as I go. All right, let's go take a look at how we do number 2 here. So off to the side, I'm going to kind of do what I was doing before for number 1. I'm going to, in fact, this one is very much like number 1 in the sense that it takes pretty much kind of the same kind of form. We're actually going to use the sign again, just like how we had z equal to 2/3 sine. In this case, I'm going to have x equal to 3 sine theta. And the reason that we're picking this 3 is because when we square this entity, we'll have the same constants, right? So that we'll have a 3 squared, 9, and we'll have a 9 minus 9 sine squared. So let's go ahead and write that. Well, first, we should probably have a dx, right? So this is very much like a u substitution. So we're going to have a 3 cosine theta d theta. So let's go ahead and do our substitution here. We still have an integral. And so we're going to have this 3 cosine from our dx d theta. But now we're going to also substitute in this x with our 3 sine theta. So we'll have that. So on the bottom, we'll have the square root of 9 minus 9 sine squared theta. And when we go ahead and simplify this a little bit, so let's go ahead and do this 3 cosine theta. And then on the bottom, we're going to pull out a 3 out of the radical, right? And this is a 1 minus sine squared, right? Theta, d theta. And using the same kind of identity that we had before, we know that that 1 minus sine squared is actually just cosine squared. So we'll have our 3 cosine theta, and then in the denominator, we're going to have theta, right? All right, so now this actually just becomes the integral. So those 3's are going to cancel, and those cosines are going to cancel. So all we're left with is the integral d theta. Right? And that's pretty easy. That's just going to be theta plus c. Right? Now, we're not done yet because we have to sub back in what theta is. So if we go back to what we had in this line, right up here, we're going to now have to do our substitution. So our theta plus c is really the arctangent, arcsine. Okay, arcsine of x over 3 plus c. Okay? And then that's our final answer. So we were able to use the methods of number 1 to kind of do a neat u substitution trick for number 2 in order to make it in terms of trig functions, which we can easily manipulate because of their properties, and then do the integral from there and then go back. That's pretty helpful. So what we're going to do now is talk a little bit about, so I'm going to go over to the next page here, and we're going to talk a little bit about the integrals that have sine to a power theta, and then cosine to a power of theta d theta. So eventually, you guys will start seeing a lot of integrals like this that take the form of sines to some power and cosines to another power, and they're multiplied together. And if you've got your book near you, I'm actually going to talk about what the little hint on page 325 if you want to follow along. So if the power of cosine, which is m in this case, so if we got if m is odd, then we want to sub out the cosine factors. So you say if it's odd, all you do is take cosine squared theta is equal to 1 minus sine squared theta, and you sub out all but one. Cosine theta. And then you're able to do a u substitution. And that will just kind of flow out and you'll be fine. Same type of deal now if we have that n is odd. So that's the power on sine. What we're able to do is kind of just the reverse. We're going to say that sine squared theta is equal to 1 minus cosine squared theta. And then we sub out all but one sine theta. And then do another u substitution. So depending on which one's odd, you're going to start trying to convert the cosine squareds or sine squareds in terms of the other one. Now, there's a third case. So if they're both even, then it's down, both m and n are even, we're going to do a separate substitution. It's the double angle formula. So sine squared theta is equal to 1/2 1 minus cosine of 2 theta. And the other one is cosine squared of theta is 1/2 1 plus cosine 2 theta. So the only difference between these two is this plus sign. We've got this plus sign here and this minus sign here. So those are the only differences between the sine squares and the cosines for the double angle formula. It might be easier to kind of remember that since cosine is like an even function, a lot of the times there's always pluses in formulas that involve them, wherein sines is an odd function, so most of the time minuses show up. That's not always true, but for this case it is. It's just something to kind of keep in mind that helps remember. Another formula they suggest you keep in mind is the fact that sine theta times cosine theta is equal to 1/2 sine of 2 theta. So this is another one. Just kind of keep in mind, it helps a lot with reducing your problem. You've got these sine to the n times these cosines to the m. Helps you reduce the order and kind of work through the problem. All right, awesome. So now what we're going to do is go ahead and go to the next page. And I'm going to put a little bit harder of a problem and give you guys a little bit about it. And we're going to go about it in steps. So this is number 3 here. And it is the integral of 1 over x to the 4th times the radical x squared minus 7 dx. Again, that's the integral 1 over x to the 4th times the radical x squared minus 7. So there's kind of like 2 steps to this problem. Get it in terms of theta, so do a trig substitution, kind of like how we did for number 2. This one is not the same substitution. It's not sine, so be careful. Kind of recognize what you've got. I'll kind of put this off to the side here. So we've got our x squared minus 7. This is the guy that we kind of want to reduce, right? And our form is variable first, and then our constant second. So this is kind of the other set of equations, not sines and cosines, but the secants and cosecants and tangents. So go ahead and try to think about this for a little bit, and we're going to go over in a few minutes. If you get to the point where you have your integral solely in terms of theta, go ahead and put that in the chat, so I know where you guys are at, and then we can try to talk about it in pieces. Because there's 2 major steps in solving this problem. All right, so let's talk about what kind of substitution we're doing here for this guy on the right. So we've got our variable squared minus this constant here. So what we want to use instead is actually secant. So let's go back and write the original identity that we were using. So we had sine squared theta plus cosine squared equals 1. Right? So what would happen if we divided both sides of this equation by cosine squared? Well, on the left-hand side, we would have a sine squared over cosine squared. So that's just tangent squared theta. Then we have cosine squared over cosine squared, so we'll just have a 1. And then we'll have a 1 over cosine squared, which is just secant squared theta. Right? So if we can rearrange this, right, we've got secant squared theta minus 1 is equal to our tangent squared theta. And this kind of takes the form of what we've got. So we've got the variable squared minus this constant. So we want to use secant instead of sine like we were doing before. So now the task is to make sure that we've got the same constant in front of both terms. So we've got the 7. 7's not, we can't take a clean square root of that, so we're just going to go with radical 7. let's go ahead and set our x equal to the square root of 7 times secant theta. Let's kind of tie that up a little bit. Okay. So with this substitution now, go ahead and take a little bit, plug this in, see what you get, and then we'll arrive at the halfway point, I feel, for this integral. There's another step that we have to do involving substitutions. So go ahead, plug those in. Give you guys about a minute. All right. So plugging this guy in now. Now it's going to look pretty messy at first, but we're gonna get through it. So we've got this. First, we have to find our dx, right? We have our dx is equal to. Let me kind of space it out a little bit here. We don't have dx is equal to our square root of 7 tangent theta secant theta d theta. Right? So now we can rewrite our integral. So we have to substitute out our dx here. There's nothing else that really cancels, so we're just going to have this square root of 7 times tangent theta secant theta all over. Now, we have x to the 4th here. So we're going to have this 49 secant to the 4th theta, and that's just our x to the 4th. This is all multiplied by our square root of, now I'm going to pull out our 7 here, and then secant squared theta minus 1. Complete the square root. And of course, don't forget our d theta. Now it looks pretty messy, but don't worry. This kind of helps out. So if we work around this, we'll notice that first, let's go ahead and there's actually 2 square root of 7s, one on the top and one on the bottom. So those are going to cancel out. So our constant is just going to be 1 over 49, right? We really don't have to worry about any of the constants here. And then we're still going to have this tangent secant on the top. Now, we have the secant to the 4th on the bottom, and this radical, this guy right in here, we're going to manipulate using our substitution. And over here, we've got this exact thing, right? So that guy is going to become just a tangent, right? Because we're taking the square root of this tangent squared, and that's going to cancel. So what we're going to be left over with inside of this integral is just 1 over secant cubed theta d theta. So as messy it really reduces to something a lot nicer. And so now what we're going to go ahead to do is we're going to rewrite this, and this is 1 over 49 cosine cubed theta d theta, right? And just because secant is just 1 over cosine, so 1 over secant is just cosine, right? So we've got 3 cosines here, and that's going to take us back to the last page, right? When we're talking about if the powers of sines are odd here. So we don't really have to worry about n here. N is just 0 in this case, right? So all we do is we have cosine to the third. So we're going to go back over to this. And this is our next big step. We're going to have to do like a u substitution on this integral to get our final answer. So take a minute for this integral, do your u substitutions, and show me what you've got in terms of u. Because the algebra afterward is a little bit tedious. We'll go through it later. Just go ahead and find it in terms of u, and then we'll go ahead and solve it. Again, if you have your book with you, the page that talks about the powers of cosine and the powers of sine in an integral is page 325. And again, don't be afraid to ask me questions. I see everyone's questions. We're going to be addressing all of them in just a little bit. Okay, so now we have this integral 1 over 49 cosine to the third theta to theta. So what I'm going to do is follow kind of the guidelines that we did on the last page here. So since we have that m is odd, we're going to make a substitution of cosines and just keep going until we only have 1 cosine left. Right? So in this case, I'm going to go ahead and pick u is equal to sine theta. And you'll see why in a second. We're going to apply the logic of the last page. So we're going to have a cosine theta, d theta. We're going to just keep that off to the side for a second. So now we're going to rewrite this integral as 1 over 49. And then, so we're going to take out one of the cosine squareds, right? And we know that that's equal to 1 minus sine squared theta. And we're going to have a leftover cosine theta. Okay. Now, this is where our u substitution is going to be really handy. Because now, see how one of those cosines is going to cancel? And we can just substitute in du. Let's go ahead. This guy right here is what we have right here. So we can just substitute that du in. That's why we make this kind of substitution. And that's why we leave one cosine and turn all the other ones into sines. So now we have the integral of 1 over 49, 1 minus u squared du. Okay. And this is a pretty easy integral. Right? So we're just going to have to take it, keep this 1 over 49 out in front, and then we'll have a u minus u to the third over 3 And let's not forget our plus c. So we've solved the integral, or added the integral. We don't have to worry about integrating anymore or any kind of substitutions and stuff like that. What we do have to worry about is going back in terms of x. So we have u, which is in terms of theta, which is in terms of x. So we're going to have to work back until we get to our final answer in terms of x. So let's go ahead and now substitute in what we had for u. So we have 1 over 49. And then we're going to have this sine theta minus sine to the third theta over 3, close brackets, plus c. Not too bad, right? So that's the first step. Now we have our final answer in terms of theta, and I think this is where a lot of the algebra gets a little intense, is going back. So we have theta, and now the thing that we had for theta was this expression up here, now in green. So we're going to have to do that whole substitution back into the sine theta. So we're going to do this off to the side, a little side work so you guys can see. Actually, go ahead and factor this a little bit, simplify it first, so you guys can see it a little bit better. So these both contain sine terms, right? So we're going to plot a sine theta, and then we're just going to have a 1 minus sine squared theta over 3. So it kind of looks like our identity, but not exactly. So there's going to be some work involved with making it look a little bit better. So off to the side here, I'm going to do some work with that. So we have our 1 minus sine squared theta over 3. This is equal to 1/3 plus 2/3. Right, that's just splitting up the 1 minus our sine squared theta over 3. So now we can go ahead and use our identity on the terms, the 1/3 and the sine squared over 3. And the 2/3 just sticks around, right? 2/3 plus cosine squared theta over 3. Right? And the more that we can keep it like cosines, the better, because we're working with secant, right? So what I'm going to do now is go back down to this bottom area and keep going. So we have 1 over 49 sine theta times the quantity 2/3 plus this cosine squared theta over 3 plus c. Okay. Now back over to the side, we're going to do some side work here. And if we look at it, what we have in green, we have this x minus the square root of 7 secant theta. Now we do have a cosine squared, which is closely related to secant. So let's try to get a secant squared and see what we can do with that. So we're going to square both sides of that green expression. And that leaves us with x squared equals 7 secant squared theta. Right? Well, let's go ahead and rearrange this guy to look more like what we want. So I should go actually rewrite this. This is still equal to our 7 over cosine squared, right? Just moving the secant into cosines. And then now let's rearrange it. So then we've got that cosine squared theta. So multiplying it over to the other side and then dividing by x squared gives us 7 over x squared. Not too bad. But now we've got this sine term that's left over. And the way to go about in getting rid of this is actually remembering that our cosine squared plus our sine squared equals 1. So if we've got the square root of 1 minus cosine squared theta, that's just sine, right? That's just rearranging our old identity. Now, let's substitute what we have for cosine squared in there. So we've got 1 minus our 7 over x squared. And now we've got all the pieces that we need to sub back into this guy. And then we're going to have to simplify a little bit, but then we'll arrive at the final answer. We have the square root here of 1 minus 7 over x squared. And that's going to be times the quantity 2/3 plus, keep this 1/3 out here. And then that's the quantity times 7 over x squared and quantity plus c. Now, there's that common 1/3 in there. I'm going to go ahead and bring that out. So that 1 over 49 is now 1 over 1/47, right? That's just, so on the denominator, we just have 49 times 3. Okay? And then we're still going to have our radical 1 minus 7x squared times the quantity 2 plus 7x squared and quantity plus c. So this is the answer. We can simplify it a little bit more. So what I'm going to do now is multiply this first term, factor out a 1 over x squared. So what that becomes is this 1 over x times the square root of x squared minus 7. So all I did there was that 1 is an x squared over x squared, and I just factored out an x squared outside of the radical, so it just becomes a 1 over x, right? So that was that first term there. Now the second term, this 2 plus 7 over x squared. I'm going to do the same type of thing, factor out x squared, or 1 over x squared, but we have no radical this time. So it's going to stay 1 over x squared. And now we've got a 2x squared plus, or I'm sorry, yeah, plus 7. Yep. Plus c. Right? And then we can just rearrange this a little bit more and it'll look a lot better. So then we've just got 2x plus 7 times the quantity radical x squared minus 7 all over x cubed. Right, and then that's our final answer. So notice how we had two major steps in solving this problem. We had this radical with these terms at the top. One that I'm going to highlight right here. So this denominator with this radical here is what we really want to get rid of, and that's why we use trig substitution. So we got it in terms of this cosine to the third, which is something that we can do with u substitution that we learned earlier on in the section of 6.2. So we used the later lessons of 6.2, the trig substitution, to get us halfway through the problem, and then the rest of it was the cosines and sine kind of substitutions from the earlier part of the section to carry us through to the end result. And the algebra at the end is a little bit tedious, but we got through it. I think this is one of the harder problems because it utilizes a lot of what you've learned in this section. If you guys have any questions specifically about the last three questions that we've gone over, you can go ahead and put them in chat or unmute yourselves and ask them. Otherwise, we can move on to questions that you guys might have with some of the homework. or I can do another practice problem. All right. So let's kind of go back to this second page here that I have. And we're going to kind of elaborate more on this table that they've got on page 328. So it's another kind of guideline system. It's highlighted. So on page 328, we have this table. So if we've got an expression that takes the form of this a squared minus our variable, this x squared, then we can try to use the identity 1 minus sine squared theta equals cosine squared theta, right? Because we've got a constant minus our variable, so this kind of takes the form of that. And then we saw that in number 2 and in number 1. But what if we have something along the lines of the square root of our variable first minus the constant that we have, right? Well, we saw in number 3 that we might want to use something along the lines of secant squared theta minus 1 is equal to tangent squared of theta, right? And that's the substitution that we used in number 3. And then there's a third case here where we have the radical of x squared plus a squared. And the ordering doesn't matter there because, of course, it's just addition, right? In this case, you can rearrange the formula secant squared theta minus 1 equals tangent squared, and then just have that tangent squared theta plus 1 is equal to secant squared theta. And now this takes the form of what we have there on the left. So if you've got radicals in your integrals that have this type of form, then we can go ahead and do these types of substitutions, right? So based on what kind of integral that you have, following these steps here will pretty much get you through the integral. Sometimes you might have to do some combinations of integral techniques. Like in section 6.1, you guys learned integration by parts. It's completely feasible to have an integral where you do a trig substitution and then get to a place where you would have to use integration by parts. And in section 6.3, you guys will learn yet another integration technique, partial fractions, which is taking something of a fractional form and splitting them up into multiple fractions that might be a lot easier. And this isn't splitting them up from the numerator, but rather splitting them up the factors of the denominator. Now, algebraically, it's a little bit more complex because you can't just have all the terms together. So we're not just doing something along the lines of, let me go to a new page here. We're not just doing something along the lines of like A plus B over X. Now, show me a white screen. Is that, okay. Okay, there we go. A plus B over X, we can just write that as A over X plus B over X. And that's splitting up the numerator into two different fractions. But partial fractions does more than that. it's splitting up the factors of the denominator. So let's say we had like some kind of quantity. We had a plus b over x plus 1. Now, this is not just simply a plus b over x plus a plus b over x plus 1. These things are not equal. So what we have to do is, let's define a new a that's over x and a new b that's over x plus 1, and find out what a and b are. And then once we have that, the integral becomes a lot easier because now we don't have these multiple factors in the denominator, but just one. And we can treat the integral separately because all the only difference here is now that there's just an addition between them. And we can split those integrals up, and the problem becomes a lot easier. So now you guys started to think we're supposed to start looking at 6.3 sometime today. Don't worry about it if you haven't yet. So you still have time. So let's go ahead and go through one of the examples here for this type of problem. Okay. Let's pick a good example. Where this is. So we've got about 8 more minutes, and I want to pick a shorter one. There might not be enough time, but let's go ahead and start and see if we can get some stuff done. Now, again, this is a little bit ahead, so don't worry too much. We're going to be evaluating x squared plus 2x minus 1 all over 2x cubed plus 3x squared minus 2x dx. So our denominator is pretty complicated in this case, right? So what we're going to do is factor out this denominator. So our denominator is actually just x 2x minus 1 and x plus 2. At first, you could see that you can just take out an x, and then it might be a little bit easier to come up with the other two parents. So don't worry too much about that. This is actually example 2 in your book for section 6.3. So if we don't finish here, you guys can actually go ahead and read that. So now we've got what's inside this integral are x squared plus 2x minus 1 all over, and now we're going to write it in our factored terms, 2x minus 1 and x plus 2. And we're going to define this new a, right? And this is going to be over x. And then we're going to add b over this other term, which is over 2x minus 1. And then this c term, which is going to be over x plus 2. All right, and the whole goal now is to find out what a, b, and c are. And if we can do that, then it makes the integral a lot easier, right? So what we're going to do is we're going to multiply both sides of the equation by this denominator here. So we're going to take this denominator right here and then multiply it across. What that will do is we'll have now an x squared plus 2x minus 1, that's the numerator that's left over, is, so now on this a term, everything but the x survives, right? So we're going to have this a times 2x minus 1, x plus 2, right? Because the x term canceled, right? And we've got this b term. So now what survived was the x plus 2 and the x. And then on C, it was the 2x minus 1 and the x term. So it's everything that the denominator wasn't for that other line. Now, we can go ahead and rearrange the this right-hand side. We've got this 2a plus b plus. So what we want to do is put it in powers of x. 2c on the x squared, right? So just go ahead and factor out that right-hand side and collect the x squared terms, the x terms, and the constant terms. So that's our x squared coefficient. The x coefficient is 3a plus 2b minus c on this x term here. And then our constant coefficient is just 2a, right? So if we have something that has this x squared, and then on the left-hand side we have this x squared, we know that those coefficients have to be equal. So what that means is for each coefficient for the x squared, the x, and the constant term, those things have to be equal, and then we'll have a system of equations that we can try to solve. So this 2a plus b plus 2c, the coefficients for this x squared are the same as this coefficient right out here, which is just 1. So this is equal to 1. So now let's look at this coefficient here. On the x term, that has to be equal to this guy. So we have 3a plus 2b minus c is equal to 2. Right? And then I'm guessing you guys can guess what's next. So we've got our minus 2a is equal to minus 1. Now, using these, we can go ahead and solve for what a, b, and c are. In the rightmost equation, it's pretty easy to solve for a, right? Then you can substitute those in for the other two and go ahead and solve those to find what a, b, and c are. And in the end, you guys can do that. We're running out of time, but I'll just write what they are. You guys can take the time and see if you can figure that out. Right. So these are what our A, B, and C are. So now we can go back and look at this line that we've got here. Let's see if we can go ahead and. Nope. Right. Let's try Dropbox here. There we go. So that equation that we've got right there, now we know what A, B, and C are. So we can convert what we have on the left to what's on the right with our choice A, B, and C. So now we can rewrite our integral in terms of a lot easier expression. Ooh, still have the lock on. All right, so now I'm going to rewrite what that fraction is. So we have our 1/2, this is A, 1 over x, right? Now B was 1/5, and that was on the 2x minus 1 term. And then C, let's make that a minus 1 over 10 on the x plus 2, 1, right? And then we can split up our integral and then do each one of these separately. And then you can do use substitutions, and you guys will be able to do each one of those individually. And then our final answer here, you guys can go ahead and do it out if you would like to. but we'll get 1/2 natural log of x plus 1/10 natural log of 2x minus 1, and then minus 1/10 x plus 2 plus some constant c. Right, and that's going to be our final answer. So that's kind of like a brief opener to partial fractions. So go ahead and look at section 6.3, get comfortable with it. So that's just another tool that you guys can use to solve integrals. So now we're at the end of the recitation. It's 8 o'clock. So I hope you guys feel a little bit better about some of the material. If you have any questions, you can go ahead and shoot me an email. I can get back to you. So now I'm going to go ahead and end the recording.